Welcome to Chapter 14, the internal processes. In this chapter, we're going to go into much greater detail of plate tectonics and their processes at plate boundaries. And then, of course, the results of the movement of plate boundaries, which include earthquakes and volcanoes. This is a map of the world. And what do you think is the biggest thing missing from this map? I would say the oceans. And so the point of this map really is to show how diverse the topography of the ocean floor really is. In fact, you can see areas of ridging, sometimes known as mid-ocean ridges, where we actually have new volcanoes forming on the ocean floor. And then we also see in areas over here, large trenches, which would be where subduction is normally found. So for this chapter, we are looking at several new terms. We're going to look into something called the hypsometry, which is relative elevation of ocean floor and continental mountains. We're going to get into different types of faults, the terms surrounding earthquakes, such as epicenter and focus, P waves and S waves, and then deal with some byproducts of volcanic eruptions, such as pyroclastic flows and lahars. One thing I want to note on this diagram, and it's because we actually live on this, is the ring of fire. The ring of fire surrounds the Pacific Ocean and includes an extraordinary high activity of volcanic eruptions and earthquakes. So if we look at hypsometry, we can take a look at the highest mountain, which is Mount Everest, at 29,035 feet. But then we can go at the other end and look at the deepest ocean trench, which is about 36,000 feet below sea level. So the greatest ocean depth is actually larger than our highest mountain. And going back a few chapters ago, we were looking at how much of the Earth is covered by water. And I believe I said that about 70% of the Earth is covered by water. What that means is there is more oceanic crust than there is continental crust. And that's basically what this diagram is showing you. It also shows you what the average elevation of the Earth is. And the average elevation of the Earth is really below sea level, about 6,790 feet. So let's take a look at the engine of plate tectonics. And we talked about a little bit of this in chapter 13. And in your book, chapter 14 goes into a little bit more in detail. We have our seafloor spreading centers and our subduction centers. Those are the two main processes that drive plate tectonics. Now, the process behind all of that, deeper within the Earth, is convection. Because of convection, we have rising magma that helps spread out the seafloor. And as the seafloor is getting spread out, once it collides with continental crust, because oceanic crust is more dense than continental crust, it dives underneath it in subduction areas. And that's one of the reasons why we have many volcanic many volcanic chains and mountains on the coast, especially along the Ring of Fire. Because as this rock is getting subducted deeper within the Earth, it melts, and that rising magma will go up to the top of the continental crust through volcanoes and seep out as lava. Now there are some general types of plate boundaries. So we're going to look at some plate boundaries in more detail. in a little bit, but I want to just point out the three major types. So let's start at the bottom actually. Convergent boundaries are two types, and we usually get either oceanic crust colliding with continental crust, which you see on the right, or two pieces of oceanic crust, excuse me, that collide together. And with that, one of the pieces of oceanic crust will actually be more dense than the other, and this creates island volcanoes. Not like Hawaii, because remember, Hawaii is being produced by a hotspot. Then we can actually have divergent plate boundaries, which includes seafloor spreading areas. And then we can have transform plate boundaries, which basically, instead of things going toward each other or away from each other, they're moving side by side. A little bit of a closer view of an oceanic continental collision is the Andes Mountains along the west coast of South America. We have oceanic crust that collides with continental crust, and because oceanic crust is denser, it dives underneath it, partially melts, and becomes magma to help provide lava for volcanic mountains. And then we have, like I said before, oceanic collisions, where we have two pieces of oceanic crust colliding, and one piece just so happens to be more dense than the other. So we have volcanic islands. And in this example, we're looking at volcanic islands north of New Zealand. Now, one kind of collision that we didn't see in the previous slide was continental-continental collision. When two pieces of continental crust collides, what you'll get, it's like taking a sheet of paper and trying to squish it toward each other, and then there's a part of that piece of paper that rises. So when we have continental collisions, we actually tend to see large mountain ranges form. The subcontinent of India has moved really quickly since the beginning of the breakup of Pangaea. Because of that, it is colliding with the rest of Asia at a pretty fast rate, which gives way to the Himalayan mountains, some of the tallest mountains on Earth. Another set of mountains that are due to continental collisions is Italy, which at one point was not part of Europe, is colliding with the rest of Europe and creating the Alps. And the Alps is again a byproduct of a very intense continental collision, and Italy is still moving toward the rest of Europe. So now what I want to do is I want to get into the certain kinds of stresses and forces at those plate boundaries. So we're getting into a little bit more detail. It's like we're kind of zooming in on these tensions, or sorry, on these stresses and forces to help us understand a little bit about how the rock at a local level will actually change due to these different collisions. So the first kind of stress and strain is called tension. Tensional forces pull rocks apart. And if those rocks are relatively malleable, it may just thin the crust. If it breaks, it'll create a fault. And we'll get into more about these kinds of faults in a little bit here. If we have compressional forces, that means these forces are pushing the rock together. It can create folding in the rock, or it can create a reverse fault. On the other hand, we can have forces that are acting on the rock in opposite directions, but on either side of the rock. And this twists laterally this rock. So we might see bending of the rock if it's a little bit malleable, or we could see a strike-slip fault, a transform fault, where no compression or tension is really found there. We just see rocks moving horizontally. In this slide, we're seeing a result of folding, at least on the top. You can see how with folding we get areas with valleys and ridges. And a lot of that does happen in nature. Now, if there's a piece of that rock that's a bit more rigid or brittle, then the forces will actually create a break in the rock, which is really what a fault is. Down here below, you're looking at some folding of rock, and you can see this because we have cut a large piece of this rock, mainly to put in freeways. So you see some on the lower left and on the lower right. A great example around here in California is taking the 14 freeway from the northern part of the San Fernando Valley up into Lancaster, Palmdale area. And you can see a lot of these horizontal folding and sometimes even some breakages in the rock because of how active the rocks are up there. Because when we get closer to Lancaster and Palmdale, we're getting really close to the famous San Andreas Fault. So let's talk a little bit about the faults themselves. So we can categorize faults into three main types. The first kind is called a normal fault, and in this case we have tensional forces. We have forces that are pulling the rock apart, but the rock is brittle, so it breaks. We have the part that actually is moving, the hanging wall side, and it's moving away and downward from the footwall. The footwall is the part that doesn't move, at least not as much. And it creates a fault plane, and over here on the right, you see in the real world what a normal fault might look like. The opposite of this would be a reverse fault, where we have compressional forces. So the rocks are being pushed together. And the hanging wall, once again, is the one that's moving the most. And this time it's moving up and over the footwall. This plane that it's showing here in these dashed lines is relatively vertical. However, if we have an area where that plane is more horizontal, we sometimes call that fault a thrust fault. The Northridge earthquake in 1994 was along a thrust fault. In fact, we call it a blind thrust fault because we actually didn't know that this fault existed until the earthquake occurred. So that's one thing about faults. We don't necessarily know where all the faults are. And sometimes we find out about faults once an earthquake occurs. And then the third type of fault, which has several names actually, is a strike-slip fault. This is due to shearing forces. So we don't have forces coming together or being pulled apart. Instead, we have forces moving horizontally. So we could have up here a right lateral fault. So if you're looking across the fault line, the areas across the fault are moving to the right, or we can have a left lateral fault. Again, the most famous, and especially around here, fault type, or I shouldn't say type, but an actual fault would be the San Andreas Fault. And in the San Andreas Fault, which is shown right here, on the western side is the Pacific Plate, and it's moving north. And that's the part that we live on, as long as you live in Los Angeles. The rest of the country, believe it or not, is on a different plate, the North American plate, and it's actually moving to the south, more or less. So we have parallel movement in opposite directions. With strike-slip faults, it can create quite a bit of linear type features. We don't necessarily get a lot of mountain building with these kinds of faults, but we get other types of evidence such as offset streams, linear ridges, and sag ponds. Probably one of the most famous offset streams is in Central California along Wallace Creek. And that is something that I usually explore in a bit more detail in the lab class. Here's just a few more diagrams describing the San Andreas Fault. If you look on top, it's showing you that these transform faults and strike slip faults are basically the same thing. And the San Andreas Fault is a right lateral fault. These transform faults are a byproduct of parallel but offset seafloor spreading centers. On the bottom, we see the San Andreas Fault, but there are many other faults in Southern California. Some are associated with that fault, but others are all by themselves. And so the San Andreas Fault is not the only fault that we have in Southern California. It is, though, the most active. Here's another view of the types of faults. Well, not really the types, just the number of faults that we have, that we know of in Southern California. There are hundreds of faults that we know of. So you might be wondering, well, how do faults create earthquakes? If you don't know already, faults are the primary reason why we have earthquakes. And along a fault, the rocks around them are moving. They are moving. Sometimes at a steady pace, but sometimes they get locked. So for example, in the upper right-hand part of this diagram, we're looking at stress along a fault. And the stress builds up because the pieces of rocks are moving, but they're locked together sometimes, but they're still trying to move. Now there's always going to be a breaking point. So once the stress is built up too much beyond the breaking point, then that stress is released along the fault. And that release of stress is an earthquake. Now keep in mind that anytime we have an earthquake, that stress doesn't really go away. It moves. So as in the diagram in the upper right-hand part, we have moved the stress a little bit away from the fault. If the stress is too much, it may break too and create aftershocks. So every time we have a large earthquake, we have several aftershocks in an attempt to sort of balance out the stress. But that stress, again, doesn't ever really go away. So eventually, even if it's not in an aftershock, that stress will once again build up and then could create an earthquake. Around here, we're mostly concerned about a large earthquake along the San Andreas Fault. The San Andreas Fault is a strike-slip fault that is not necessarily unique. In northern Turkey, just south of the Black Sea, we have the North Anatolian Fault system. And there were two major earthquakes in a relatively short time period back in 1999. And other areas along the Ring of Fire can actually have these types of transform faults. It just happens that Turkey is not part of the Ring of Fire, but it just goes to show that lots of places around the world, especially along plate boundaries, are prone to earthquakes. So a little bit about the anatomy of an earthquake. So on the top here, we're looking at the Loma Prieta earthquake of October 1989. This devastated parts of the Bay Area. What's interesting about this is that the epicenter of this earthquake was quite far away from San Francisco, but because of how large the earthquake was, it still devastated parts of San Francisco, Oakland, and the Bay Bridges. Now, for some terminology. Most people have heard of the epicenter, but many people don't really know that the epicenter isn't the actual true source or origin of an earthquake. Something called the focus is the true origin of the earthquake. The focus is the point beneath the surface of the earth where the shaking and the movement along the fault originated. The epicenter is just the location directly above the focus that's on top of the surface of the earth. So that's a key difference there. Other times you'll hear terms like P waves and S waves. So P waves are the primary waves of earthquakes, and they're the first waves that emanate from the earthquake. And they shake the rock horizontally, they push and pulls rock. Afterwards are the more destructive S waves or secondary waves, and they create some of the rolling motion, vertical motion of the crust. And that again can be some of the most destructive waves. Probably what is responsible for the collapse of some of the bridges around San Francisco in the Loma Prieta earthquake of 1989. There is a rating system for earthquakes that many of you are aware of because we live in an earthquake-prone area. Some people don't realize that the magnitude of earthquakes aren't in a linear scale. They're actually in a logarithmic scale. So when you go from one magnitude to the next, the amount of energy that's released is 32 times greater. So a magnitude 8 earthquake is not twice the strength of a magnitude 4. It is 32 times that for every magnitude, and another 32, so it compounds it. So that's why you might have, and I'm not going to get into the details of the math behind this, but you might have a 3.0 earthquake and barely feel it. If you have a 5.0 earthquake, you would feel it. If you have a 7.0 earthquake, there could be large devastation. Now, the Richter scale actually helps seismologists calculate the magnitude, but the Richter scale is slightly different from the moment magnitude scale. So just keep that in mind when I show you additional earthquake statistics. So here's a sampling of significant earthquakes going back to about 500 years ago. The deadliest earthquake that we know of occurred on January 23rd of 1556. It killed 830,000 people in China. Now back then we didn't really have a way to rate these magnitudes. Some other interesting ones along this list, and feel free to read this through. The 1906 San Francisco earthquake was the largest earthquake along the northern San Andreas Fault in modern times. And it killed 3,000 people, and it devastated half of the city. Southern Chile and southern Alaska, these two earthquakes are some of the strongest that we've ever seen on Earth. And you should see pictures of southern Alaska when this occurred. It looked like it took the town, some of the towns in southern Alaska, and then just turned it upside down. It's very terrible. Closer to home, we had the 1971 San Fernando earthquake, which killed 65 people and was a 6.7 on the moment magnitude scale. Then we had the Loma Prieta earthquake in 1989, and then of course the famous Northridge earthquake of 1994, very close to home. It was only a 6.8, which is strong, but unfortunately we're looking at the possibility of a much stronger earthquake along the San Andreas Fault relatively soon, because the southern part of the San Andreas Fault has not ruptured in a major way since the late 1600s, and so we're pretty overdue. Some additional ones that were devastating. We have the Port-au-Prince, Haiti earthquake of 2010. We also have the quite famous 2011 Japan earthquake and tsunami, which together killed about 30,000 people. And that earthquake was a 9.0. And because it was on the sea floor, it also created a very devastating tsunami. We'll talk more about tsunamis in chapter 20. This map shows you the general earthquake hazard across the United States. And as you can tell, we live in one of the highest hazard categories that you can find in the country. Other areas that have a lot of earthquakes include the Big Island of Hawaii, due to the volcanic eruptions, southern Chile, and even parts of the Midwest, from southern Illinois through Arkansas and parts of Tennessee and Kentucky. This is due to the New Madrid Fault, and this is a part of the Midwest that actually has a potential for a large earthquake. When I show this map, I often ask my students, where would you rather live if you want to minimize your natural disaster potential? If you include tornadoes, hurricanes, volcanoes, tsunamis, and earthquakes, then basically the spot in our country that might be the best would be up here in the very northern parts, like North Dakota and Minnesota. Of course, there may be other reasons why you wouldn't want to live up there, because if you're used to a large city, it's quite desolate up there. I love this picture. Now, I didn't take this picture, of course, but this picture again is from one of my favorite spots on Earth, Iceland, and it shows geysers, and these geysers are basically are there because of volcanic activity underneath. But in the background, you see the northern lights. So what I want to talk about now, I want to talk about volcanoes. We're going to get into different types of volcanoes and some of its hazards. This is another really interesting volcanic eruption picture, because we see the eruption cloud, but we also see other clouds that are being formed due to the rising heat of this magma, of this ash and smoke. And sometimes we can get clouds forming on top of eruptions. So the settings that we need to have for volcanic eruptions, we've already talked about being near plate boundaries, and that still is one of the best ways to get volcanic eruptions. Sometimes, though, we can get volcanic eruptions when continents are being pulled apart. We can get your chain of volcanic mountains along the coast if we have a subduction zone. We can get seafloor spreading and its volcanic activity due to, well, seafloor spreading centers. And then we can also get subduction zones in the ocean that create island archivolcanoes. And so the one type of volcanoes, once again, that we can get without plate boundaries are due to hotspots. Volcanic activity in general, if you look at the large time scale of the Earth, 4.6 billion years, volcanoes are temporary features of the landscape, and they're actually really necessary for life on Earth because they have provided much of the water vapor that we have in our atmosphere. Also, once volcanoes are starting to let's say disrupt the plant life and sort of scour the landscape, we have new nutrients and elements required for sort of a renewal of plant growth. So let's start talking about volcanic types. Because the magma and the lava that spew out of the volcanoes are different from one volcano to another, we get different types of volcanoes and the shapes of volcanoes can be different. If we have a shield volcano, which is what we have in the Big Island of Hawaii, we don't have large volcanic peaks. We can get relatively flat volcanoes. And that's because the viscosity of the magma, the ability for it to flow relatively easily, the viscosity is very high. Or no, I'm sorry, the opposite. The viscosity is low, and the ease at which the magma and the lava flow is relatively high. So it doesn't take much for the lava to flow right out of the peak of the volcano. And so that doesn't really create much of a structure, much of of that cone structure that you might see in many volcanoes. You have very little pyroclastic material, which I'll talk about in a little bit later. And it's not that dangerous because it is so fluid that it just spews out at a relatively nice rate. On the flip side, when we have more silica, which makes lava and magma more viscous, harder to flow out, then we start to get a buildup of your magma, and we can get magma chambers, and these magma chambers can help create and solidify the characteristic cone shape of a volcano. What that also means is that the lava doesn't flow out of it very easily, so it builds up over time. And that pressure will build and build and build until it no longer can be withheld, and then it erupts, and it can erupt quite violently. And this is a much more dangerous type of volcano. When the lava gets very viscous, then it may not actually erupt. It'll just create what's called a lava dome. And instead of the lava erupting, it could actually just put a lot of pressure on the sides of the volcano. Sometimes those sides will become destabilized and collapse. And that's what a pyroclastic flow can be, which basically is just sort of an avalanche of hot gas and ash flowing down instead of up into the atmosphere, down along the sides of a volcano. And we have some of that here in California. What is nice is that the San Andreas Fault, which is a transform fault, isn't really conducive to volcanic activities, but when you get farther north into California, we can get more of these volcanoes. Cinder cones are very much like your composite. They're the larger cone-shaped and dangerous type of volcanoes. And they are typically found associated with other volcanoes. And then we can get volcanoes that have collapsed. So due to a major eruption, they have collapsed, and the peak of the volcano is gone, and you just have a crater. And in the case of Crater Lake, which is in Oregon, that crater has filled in with water over time, mainly through precipitation. This lake is the deepest lake in the United States. At places, it's 2,000 feet deep. And it's probably one of the most famous calderas, which is the type of volcano this is, in the world. So with volcanoes, we have volcanic hazards. Some of the most common volcanic hazards that you might know about are the gases that come out of volcanoes. And these gases may temporarily alter the climate around it, and it's very temporary and it's very localized. We also have lava that will flow out of these volcanoes, and then probably the most famous type are the eruption clouds. Now the eruption clouds can include gas, but most of the time it's ash and soot, and it can travel large distances. These eruption clouds can even carry large rocks and throw these rocks very far away from the original source, and that's why sometimes these large rock fragments are called bombs. In addition, we have those pyroclastic flows, one of the most dangerous parts of a volcano. These are hot gases and hot gases and other material that flow down like an avalanche, and it can travel up to 100 miles per hour. So it's very hard to outrun these pyroclastic flows. When volcanic lava mixes with rain or snow, we can get lahars, which are basically mud flows. And they, of course, can be very dangerous. So this diagram here shows a very good comprehensive overview of some of the hazards associated with volcanoes. We can get a lava dome collapse. We can get an entire side of a volcano collapsing, which is what happened with Mount St. Helens. These rocks right here, they're called bombs. We have the eruption cloud. And when some of that eruption cloud mixes with rain and there's gas in it, we can have acid rain. Unlike earthquakes, which have very little, earthquakes in general have very little to no warning. We can monitor volcanic hazards and have an idea of when the next volcanic eruption will occur. One way to do this is to actually look at the landscape around a volcano to see if we see previous volcanic flows in the way of pyroclastic flows. That way we have an idea of what type of volcanic hazards will come from an eruption. We also have something called tilt meters, and when the volcano is about to erupt, the magma that's trying to get up into the volcano will cause the volcano to swell a little bit. In addition, one of the best ways to assess volcanic eruption potential are the series of minor earthquakes that typically occur before an eruption. Down here below is a picture of a lahar, a major mud flow that flowed from the source of the volcano and devastated some of these, unfortunately this impoverished community. And one of the best success stories of a volcanic eruption was Mount Pinatubo in 1991, which was predicted to erupt, and it really did erupt around the time that they thought it was going to erupt, and they were able to evacuate many thousands of people ahead of time and to save thousands of lives.